So we need to talk about chemical reactions. And much of this should be review. If we come to a point where you're just like, I don't know what you're talking about, please stop me and I'll elaborate more. I don't want to bore you if you already understand a lot of this stuff. So a chemical reaction is something in which we have one or more substances being changed into other substances. Basically, a chemical reaction involves a chemical change. Okay? Chemical change, one substance being changed into another. These chemical reactions just involve rearrangement and exchanges of atoms. It's like building with Lego blocks. You take one or two little buildings and you take them apart and you make it into a horse and a dog. The bricks have not changed. The atoms have not changed. What they are doesn't change. How many there are doesn't change. We're just rearranging them. The atoms do not get changed. The compounds do. Okay? Very important to understand that. So a chemical equation is just our shorthand way of describing a chemical reaction. And it has this basic form. We have reactants and an arrow. So the reactants do something and they lead to the products. The reactants react to produce the products. So reactants are on the left side, products are on the right, because we read left to right, and so we write our equations left to right. These equations give us a lot of information about the chemical reaction in a very concise form. They're going to give us the chemical formulas and the states of those reactants and products. They're going to tell us the relative numbers of molecules of each of the reactants and products. And we can use these chemical equations to figure out the masses of reactants used and the masses of products produced. And so this becomes very, very practical. These are the symbols. They're sometimes called state symbols that we use to indicate the physical states of reactants and products. So G for gas, L for liquid, S for solid, AQ stands for aqueous, which means that it is dissolved in water. And we discussed that a little bit with the acids yesterday. Acids are actually covalent compounds, molecular compounds, but when they're dissolved in water, they form ions, and then we call them acids. So that's what those symbols mean. So let's look at an example reaction. The combustion of methane. Methane is natural gas. It reacts with oxygen and burns. We've lit our Bunsen burners. This is the chemical reaction that was occurring. Whenever something burns, it involves oxygen. So there's oxygen in the gas state, in the air. I think we all recognize that if there's no air, things will not burn. It's the oxygen in the air that's necessary for combustion. So here we have the formula for methane, CH4. You are not expected to know that yet. And this is reacting with oxygen. The products that are formed, what's the name of that guy? Carbon dioxide. And this is water. He goes by his common name. So if we look at this and we think about carbon atoms and hydrogen atoms and oxygen atoms, we can't have atoms appearing out of nowhere, and we can't have atoms disappearing. So there's a problem with how this equation is written. Here we've got 2 oxygen atoms, and in the products we have 2 oxygen atoms here and 1 over here. We have a total of 3. Where did the extra oxygen atom come from? Well, it's not a balanced equation. This is not describing what's actually happening. It's giving us the identities, but it's not telling us the ratios in which they combine. The other issue with that equation is that on the left we have 4 hydrogen atoms, and on the right we have 2 hydrogen atoms. You might say, well, how about if we just make those 2 hydrogen atoms into an oxygen atom? Problem solved. We can't do that. In chemical reactions, atoms are unchanged. So we would say that this equation violates the law of conservation of mass. We can't have mass being created or destroyed. We can't have matter being created or destroyed in a chemical reaction. So we need to adjust our chemical equation, which is just our description of what's actually happening. By adjusting the equation, that does not affect the actual reaction at all. It's just our description of it. So we say we're going to balance the equation. When we balance equations, we can put numbers, oh, I don't want to look at that one. We can put numbers in front of the formulas. Those are called coefficients. We can't change the subscripts. If you change the subscripts, you're changing what compound it is, right? It's tempting sometimes, but you can't do that. So we need to adjust the number of molecules. So here we have models showing here's a methane molecule and 2 oxygen molecules. And that's going to make 1 carbon dioxide molecule and 2 water molecules. When we put these coefficients here, 2 and 2, in front of these formulas, now we're going to end up with the same number of red, white, and black balls on each side of the arrow. Here we have 1 carbon, and over on this side we have 1 carbon. Here now we have 4 oxygens, and over here we have 4 oxygens. It's like taking Lego buildings apart and putting them back in different combinations. Here there are 4 hydrogen atoms, and over here there are 4. They're split up now and they're bonded to oxygen. And that's evidence that we have a chemical reaction. The atoms are being combined in different ways. But the number of atoms of each element remains the same. And so when we're balancing a chemical equation, we are just sticking numbers in front of the formulas so that we end up with the correct number of atoms on each side. So some people like lists of instructions, and if you're one of those people, here's your list. How do you balance the chemical equation? Well, first you write a skeleton equation with just the formulas. Really important to get those formulas correct. If you get the formulas incorrect, it may be impossible to balance the equation. Next, we're going to balance the atoms. This method is called balancing by inspection. And what they're giving you here is a guideline. You don't always have to do it this way. This is not always the easiest way, but generally. So they recommend balance the atoms that occur in more complex substances first, and balance those atoms in compounds before the atoms in pure elements. So let's go back real quick here. In this equation, we have oxygen here as an element. When we balance this, we want to leave oxygen for the end, because when we change the coefficient on oxygen, all we affect is the number of oxygens. When we put a coefficient on CH4, we change carbons and hydrogens. And so do all the compounds first and leave the elements for last, generally easier. So that's kind of number 3. Leave the free elements last, if there are any. Then look at your coefficients. Sometimes we end up with coefficients that are fractions, and we need to clear those out. Basically, you're going to multiply by the denominator of the fraction, and then check to make sure that it is in fact balanced. So let's do an example. In the cylinders of a car's engine, octane is one of the many components of gasoline. It mixes with oxygen from the air and burns to form carbon dioxide and water. Write a balanced chemical equation. Well, we need the formulas first for the reactants. What's one of the reactants? That hydrocarbon octane, which has the formula C8H8. Now, this doesn't specifically tell us to include state symbols, but let's go ahead and try to do that. So, in the cylinder of your car, this hydrocarbon octane, what do you think its state is? Okay, we'll put liquid. We could argue either liquid or gas. So it mixes with oxygen from the air. What's the formula for oxygen? O2. Okay, this is where those diatomic elements, horses need oats for clear brown eyes. When any of those 7 diatomic elements shows up as an element in a chemical equation, the formula has a subscript 2. So O2, what's the state of oxygen? It's a gas. Our clue here is from the air. Burns to form, so this is the arrow. Carbon dioxide, what's the formula for that? CO2. What do you think the state of CO2 is? A gas. And water vapor. So water is H2O. Vapor tells us that the state is what? A gas. So that's the first step. We've got the reactants and products. We've got their correct formulas. Now we're going to look at this, and I'm going to show you one method that some students really like. Some of you who have done this many times before, you can just balance this without writing much stuff down. But I'm just going to show you a thought process and a way of keeping track of what you're doing that can help you maybe when you come to a difficult one. So let's draw a line down the middle here. And on the left side, I'm just going to list the different elements. So there's carbon, and there's hydrogen, and there's oxygen. The order in which you put them really doesn't matter. I'm just going to keep track of how many of each we've got going on here. So before I start adding coefficients, I'm just going to count them up. And under this formula, I'm going to write down how many of each of these I have. So this tells me I have 8 carbons and 8 hydrogens. So I'm going to put an 8 here, and an 8 here, and a 0. Under the oxygen, in this molecule, I have 0 carbons and 0 hydrogens and 2 oxygen atoms. In carbon dioxide, there's 1 carbon, 0 hydrogens, and 2 oxygens. And in water, 0 carbons, 2 hydrogens, and 1 oxygen. When this equation is balanced, if we add up this row on the left side, it should equal this row on the right side. Now, on the left, we have a total of 8 plus 0, 8 carbons. On the right, we have 1. Obviously, this is not a balanced equation. Oxygen appears as an element, so we want to leave oxygen for the end. You could start with hydrogen, you could start with carbon. It doesn't really matter. I tend to start with the first element first. Sometimes when you're balancing equations, you might start with carbon, and you go through and you realize, oh, I'm getting in circles here, this is getting ugly. Don't force it. Stop, start over with a different element, because sometimes it's much easier if you do it with a different element, and you can't always tell by looking which one would be the best. Let's just start with carbon. So on the left side, I have 8 carbons. I can't make that smaller, really. The best thing to do is to increase this. Each of these has 1 carbon. If I put the number 8, if I put an 8 in front of CO2, then I have 8 of these units, right? So now I've got 8 carbons, so I'll change that. And I have 8 times 2, I have 16 oxygens. So now I look and I see, okay, I've got 8 carbons on the left and I have 8 carbons on the right. Carbon is good. Let's go on to the next element. So we look at hydrogen. 8 hydrogens plus 0, 8 on the left. And over here I've got 2 hydrogens. How can I make a 2 into an 8? Multiply by 4. So I'll put a 4 here. And that's going to change the number of hydrogens and the number of oxygens. So my carbons are balanced, my hydrogens are balanced, because when I put this in here, I did not mess up the carbons. Sometimes when you change this to fix one thing, it'll mess up something you already fixed, then you have to go back and fix that again. That's how you can end up going in circles. But it didn't happen this time. So here's oxygen. I have 2 on the left side, and how many on the right? 16 plus 4, 20. So if I put a 10 in front of the oxygen, then I'll have 20 oxygens on the left and 20 on the right. So that's our balanced chemical equation. I didn't end up with any fractions. The other thing that I should point out is these coefficients, to have the best form of a balanced chemical equation, the coefficients should be the lowest ratio. This would be a 1. Again, chemists have a thing against the number 1, so I'm not going to write a 1 there. But we understand that there would be a 1 there. If it was 0, we wouldn't write that guy at all. So 1 to 10 to 8 to 4. Because of the 1, you can't just divide all of those by 2. So that's the lowest ratio. Any questions? Let's do another one. Remember that picture of that statue? We talked about acid rain. So here is what's happening there is we've got aqueous nitric acid reacting with calcium carbonate to form carbon dioxide, water, and aqueous calcium nitrate. Write a balanced chemical equation. So we're going to have to take these names and translate them into chemical formulas. Nitric acid. What's the formula for nitric acid? HNO3. Nitric acid is an oxyacid. We know that because it doesn't start with hydro. Nitric comes from nitrate. Nitrate is NO3 minus, and so it's got 1 hydrogen on it. Nitric acid, and that's aqueous. And that's going to react with calcium carbonate. Okay, that's one of those ionic compounds. Calcium. What charge does calcium ion have? 2 plus. What's the formula for carbonate? CO3. And what's the charge? -2. Oh, +2 -2, so that one's going to be easy, right? Just one of each, calcium and carbonate next to each other. What's the state of calcium carbonate? Solid. You kind of have to infer that from the problem here. We're talking about destruction of a marble statuary, a marble statue. Is a marble statue a solid? Yeah. So the calcium carbonate is in the marble. So it reacts with that to form, there's our arrow. Okay, I'm probably going to run out of room. It's very common. Carbon dioxide. What should we put for the state? Gas. Carbon dioxide is a fairly large component of air. Water. This is at room temperature, so the water is going to be a liquid. What do you do when you run out of space? Well, you just go down a line. Plus calcium nitrate. Okay, now we're not dealing with nitrate. We still have the carbonate. We have the calcium and nitrate. So that's going to take 2 nitrate ions. So calcium nitrate. And what is the state that we're told? Aqueous. So we got our formulas. Now we need to balance it. So for this one, I'm not going to do the tally thing. I'm going to show you how you just kind of do it by looking at it. Do we have any elements that occur by themselves? No, we don't. So there's nothing that we specifically have to leave for last. What do you want to start with? Nitrate. Okay, so here we have a nitrate ion, and here we have nitrate ion. That's a polyatomic ion. In this reaction, it stayed together, didn't it? So we can balance polyatomic ions as units. It's like this is that bundle pack from Costco, and we bought 2 of them and we separated them, but we didn't undo the shrink wrap. Okay? It's still packaged together, and so we can balance them together. That's kind of a shortcut. If you want to balance them separately, go right ahead. So if we look at nitrate as a unit, there's 1 NO3 here, and over here there's 2 NO3s. So that tells us we need to put a 2 in front of the nitric acid. Where would you like to go next? Calcium. Okay. So here we have 1 calcium, right? And on this right side, how many calciums do we have? 1. Cool. That one's fine. Let's look at this carbonate. So here we had carbonate. That's a polyatomic ion. Is carbonate intact on the right side? Do you see a CO3? No. So that means we can't balance it together. We're going to have to look at the carbons and the oxygens separately. So let's look at carbon. Here's 1 carbon. And over here, there's 1 carbon. That's a C, but that's calcium. So the carbonates are, the carbons are okay. So we've checked NO3, we've checked calcium and carbon. Oxygen is all over the place, isn't it? So let's ignore him for now. Let's check the hydrogen. We haven't looked at hydrogen yet. How many hydrogens on the left side? 2. And how many on the right side? 2. Okay. So now we're going to count up oxygens and cross our fingers and hope that everything's okay. Because we have oxygens in here and all over the place, I think it's best to count these. Well, you wouldn't have to, because these oxygens are taken care of over here. So as long as you ignore both of them. So we have oxygens here, how many? 3. And then the oxygens that aren't in nitrate are here. That's 2 plus 1 is 3. And those guys were with these guys. So we're balanced. Any questions?